Feedback at the very end, we can circle back to it, but for now, we will be moving on to the next team.
Hey guys, I'm just gonna share my screen real quick. All right, everyone can see the slide, correct? I'm assuming so.
Yep.
Awesome. So I'm Celeste Dia, Chief Engineers with the Emergency Response Unit. I just want to thank everyone for being here again. And we'll start with our presentation. So first with our table of contents. First, we're going to go over our mission profile and our communications. Then after into our requirements, then talk about our design candidates, taking a look at our landing mechanism, retrieval mechanism, and drivetrain. Then we'll also take a look at the weight and power analysis, and then end off with our hardware and software teams. So the Emergency Response Unit mission profile. Once we are deployed from MAC, we will autonomously navigate our way to the hiker. Once we are there, we will then manually prepare and load up the hiker, switch back to autonomous to navigate our way to the extraction point, where we will then manually transfer the hiker to MEA and then go on our way navigating to headquarters. At the same time, we will be sending the communications to and from GCS to the vehicle. So here we have our first requirement. The vehicle shall be able to survive an in-flight drop from the multi-role aircraft. The vehicle shall interface with MAC, and the vehicle shall be able to slow down during descent and be able to operate after surviving a drop of X feet from MAC, and also withstand an XG load upon impact. The vehicle shall also detect the correct landing orientation, that orientation being the wheels contact on the floor. ERU2, the vehicle shall drive up a 30% grade hill at a 1.5 miles per hour while fully loaded. Derived from there, we have the vehicle shall be capable of producing a minimum speed of 1.5 miles per hour. The motor shall have an output of a minimum and maximum of X feet times pounds amount of torque to drive up the hill. The vehicle shall have the ability to travel up the hill with X pounds of weight fully loaded. ERU3, the vehicle shall be capable of autonomous waypoint navigation. Derived from there, we have the vehicle use the target coordinates from GCS. The vehicle shall be able to detect and transmit the current location and orientation, and the vehicle shall support autonomous navigation real-time processing. ERU4, the vehicle should detect and avoid obstacles such as rocks and trees along its path. The vehicle shall be able to detect these obstacles within a length, width, and height inches, and shall detect the obstacles with a minimum of X feet. The vehicle should autonomously navigate to avoid these obstacles, and the vehicle shall have a minimum response time of X seconds and shall also have sensors in order to detect these objects. ERU5, the vehicle shall be controlled via GCS. Derived from there, we have the vehicle shall be able to transmit feed wirelessly to GCS and maintain a signal at a maximum of X feet. And the vehicle shall be able to send and receive a maximum and minimum X bit rate to establish a stable communication with milliseconds of latency. And the vehicle shall be able to switch between autonomous and manual mode. The vehicle shall transmit a video feed to GCS during manual navigation. Derived from there, we have the vehicle shall be able to transmit the video wirelessly to GCS, and the vehicle shall have a minimum of one camera, and the vehicle shall capture a video feed. ERU 7, the vehicle shall be capable of preparing an immobilized hiker for transportation. The vehicle shall be capable of preparing a hiker of a maximum of 0.4 pounds. And the vehicle shall not further harm the hiker. And the vehicle shall be able to transport that hiker to MEA while safely holding the hiker during transportation. And the hiker lying flat on the ground shall be rescued. ERU 8, the vehicle shall have a range of 1,800 feet fully loaded. Derived from there, we have the vehicle shall have a minimum power of milliamp hours to travel the required distance of 1,800 feet with the hiker, and the battery shall provide an X amount of milliamp hours to the entire system throughout the mission. ERU 9, the vehicle shall have a maximum dimension of 12 by 7 by 7 inches and also have a weight of 8.5 pounds unloaded. The vehicle shall have all core electronic components on a removable tray, and derived from there, we have the vehicle shall process a removable electronics tray that will be secured for duration of the mission. And the vehicle components shall not block or disrupt the communication signals. Last slide for the requirements. ERU 12, the vehicle shall be capable of transporting a hiker of 4 inches. And ERU 13, the vehicle shall be able to operate in weather conditions consisting of sunny to overcast, no rain to light rain. Derived from there, we have the vehicle shall have an IP rating of no less than IP54. And ERU 14, the vehicle shall transmit health and status information to GCS at a rate no less than 1 hertz. Now I will pass it on to my mechanical lead, Corey.
All right, can everyone hear me? You guys hear me okay?
Yes.
Yes, we
Yeah, we can hear you.
Yep.
Okay, awesome. Hello, my name is Corey Gao. I'm the UGV mechanical lead, and now I will be going over ERU mechanical subsystem architectures, which includes our landing mechanism, retrieval mechanism, and drivetrain candidates. We will now begin with our landing mechanism candidates. Last year, we considered a single parachute versus a sacrificial platform and decided on the single parachute. This year, we will be building on top of this comparison by looking at single parachute versus multiple parachutes. Beginning with the single parachute candidate, some key attributes include a single parachute setup and an anchor point located at the center of gravity of the vehicle. Next, the multiple parachute candidate is a multiple parachute setup and allows for anchor points at the vehicle's center of gravity or corners. Through our research, the single parachute offers advantages that include a lesser likelihood of entanglement and an easier deployment compared to the multiple parachute option, which has a higher chance of entanglement and costs more while offering the same performance as a single parachute, which resulted in our decision that the single parachute would still be the best choice. And now we will move on to our retrieval mechanisms. Our 3 retrieval mechanism candidates are as follows: the conveyor, the rescue net, and finally the scooper. Beginning with the conveyor, it's a conveyor belt retrieval system that positions a hiker on a separate detachable stretcher that gets taken away by the MEA. Some of the concerns with this design include that it has low precision, low security, and concerns with long hair and loose clothing getting caught in the mechanism during operation. Moving on to our second candidate, the rescue net, which manipulates a net under the hiker and lifts the hiker with ease. This design minimizes pinch points, has good security, and a reliable retrieval. In addition, this design has a simple detachment method where MEA can pull the net off the grooved rods, or the ERU can place the net down gently in the medevac bay of the MEA and just drive away from it. One of our concerns is being able to pull the net under the hiker successfully. The final feature of this design is what we call the turret arm system. This system allows a turret-style swivel like on a tank, and arms that give us the vertical motion we need. The turret arm system has also been adapted for our final candidate, the scooper. This design scoops the hiker by pushing the thin platform under the hiker and then securing and protecting the hiker with the closure of the protective cover. This design has a more complex attachment method than that of the rescue net. An off-center placement of the mechanism allows for more room for components such as sensors and cameras, and the stretcher platform can be detached for pickup or placed into the medevac bay of the MEA. We can rule out the conveyor design due to concerns for the safety of the hiker, and between the other two designs, we have not made a 100% clear decision due to the closeness of the scores in our trade matrix and the sensitivity of the scores that was found by just playing with the numbers and seeing how the final scores reacted. Our next steps for the retrieval mechanisms will include prototyping and testing designs and then redesigning. And we will now move on to our drive chain candidates. Shown here are our drive chain candidates: single/dual Ackermann turning and differential turning. Single and dual Ackermann turning allows us to effectively implement suspension, which provides terrain absorption and a better ride quality. This drivetrain allows for high maneuverability when turning and can implement two-wheel drive and four-wheel drive. Our next candidate is differential, also known as tank turning. This design allows for a zero turn radius by having the ability to pivot around a midpoint midway between the drive wheels. It is mechanically simpler than the Ackermann, reduces drivetrain losses, and is easily capable of two-wheel drive and four-wheel drive. After condensing our trade matrix, we chose the single Ackermann as our go-to. And now I'll pass it on to Daniel Menkier to discuss electrical.
Hi, my name is Daniel Menker, and I'm here to discuss about the electrical aspects of the unmanned ground vehicles. So here we have the weight analysis of the component that'll be on the vehicle. As a disclaimer, these parts may or may not be included in the final product of our vehicle, but are provided to show a rough estimate of what the electronics on the final vehicle will look like. The only parts that aren't included in these calculations are the camera to send video feed to ground control stations, some servo motor controllers, the battery to power these components, the Raspberry Pi, and 4 other servo motors, as we are still looking into these components to fulfill these roles. We are also still analyzing the benefit of using either 1 or 2 motors to rotate the vehicle's wheels. So we have 4 graphs for 2 situations, using 1 motor to rotate the wheels and using 2 motors to rotate the wheels. Each situation has its own pie graph for weight analysis and power analysis, and we'll be covering power analysis later. So for now, we have our weight analysis here. Our electronics end up being around 0.91 pounds for 1 motor and 1.15 pounds for 2 motors. In both situations, much of our weight is taken up by the motors that'll end up powering or rotating the wheels on the vehicle and the ultrasonic sensors that we plan on using on this vehicle. We plan on using around 3 ultrasonic sensors, which each weigh around 0.13 pounds, so that we can accurately detect and avoid obstacles in the vehicle's way, which is why the ultrasonic sensor category ends up being such a large category of the weight. With this information, it's much easier to calculate how close we are to the maximum weight of 8.5 pounds, which helps fulfill requirement ERU 10. Next slide, please. For power analysis, our electronics end up consuming around 1,430 milliamp hours for 1 motor and around 2,097 milliamp hours for 2 motors, where the motors that spin the wheels end up consuming the most current out of all of these components. With this information, looking for a battery is simple, as we just need to find a battery that has more than either 1,430 milliamp hours or 2,097 milliamp hours, depending on if we use 1 motor or 2 motors, which helps us fulfill requirement ERU 8.01 and ERU 8.02. Now I will hand it off to Lewis to present the software side of our vehicle. Thank you.
Hello, my name is Louis Nguyen. I am the UGV software lead, and I'm going to be presenting our research into utilizing a robot operating system, ROS, to be the communication layer between our simulated and hardware robot, and between our data analysis software MATLAB and modeling environment Simulink. So users in the ROS network can send messages to each other. So MATLAB can send messages to Simulink or to the simulator, and then the simulator can send messages back to MATLAB. And we can process that data in many different ways. We can analyze that and verify test results from it. So the 3 ways we can go about this is, the first way is to run the simulator, run the hardware robot, and gather the data in a test run. And then once we have that data, we send the message over a ROS bag, as a ROS bag over the ROS network, and then we analyze that data in MATLAB. So we can graph that data, whether it's for torque calculations, it's for analyzing the stability of a PID controller, and we can do that to ensure that the pickup system is accurate and any other systems that need to be fully autonomous. And then also the second method would be to use a live connection test, which is to connect directly with MATLAB to the simulator or to the hardware. And then if we're doing that, we can edit the parameters in real time. So for PID controller, we can edit and check the overshoot in the robot. We can also check any other parameters for the autonomous system that needs to be secure and verified. And then once we've gone through and refined our design, refined our parameters in the algorithm, we can move to deploying on a ROS node that forgoes the MATLAB dependencies as an input to our simulator and to our ROS network as a user, and then we can fully deploy that on our robot. And the great thing about ROS is that it's an open source network. And so many other people have already developed algorithms for various other robots. And so we can utilize their algorithms and test to develop our own algorithms for our own purposes. Next slide, please. And so these are just many of the different aspects and toolboxes that MATLAB and Simulink offer to our research. So the most important ones are the control systems ones. So we can develop our multiple input, multiple output, or single input, single output controllers. And these controllers are used to verify our autonomous systems and to check the precision of our pickup system to make sure the hiker is not in any danger in any way. And so once we have these controllers built, we can test it on our simulator, WeBots, a 3D virtual world that has physical properties. And we can test it in different environments on WeBots and test its autonomous modes and accuracy. And then we can work with those to develop our prototypes. And other aspects that MATLAB uses that we're not currently working with yet, but also into application purposes and to further analysis would be some image processing, image acquisition, and computer vision toolboxes, which is all beneficial for our autonomous system. And one thing to note is that this is for research purpose. The ROS network is more harder to implement, but there's also other methods on Simulink that are easy just to go by. If this doesn't work out, we can work with embedded coders on Simulink to upload straight to Raspberry Pis or FPGAs. We can also work with TCP as a way to interface to our simulator, but all these things are a way to verify our prototypes and our software. And I will hand this off to Mario, our embedded lead.
Hello, everyone. I'm Mario Molina, this year's embedded lead for UGV. As the UGV's embedded team, we're looking to create a control system for the ERU and all of its components. This control system will be an array of custom hardware description, drivers, C, C++ applications accumulated onto a field programmable gate array, or FPGA. A dual input system will allow us to offload components that are ill-suited for FPGA implementation to a Raspberry Pi. This dual input system will run on a Linux operating system for both the Raspberry Pi and the FPGA ARM processor. The diagram you see to your left shows a flowchart of creating a software/hardware concurrent design through pre-established intellectual properties, so think processors, and our own software/hardware development, think pulse width modulation modules. Of course, there are many steps to this process. It deserves its own slideshow, but essentially we can harness the resourcefulness, the versatility, the speed of an FPGA to drive our ERU components through this process, all while not reinventing the CPU. On to our next slide. I'd like to bring your attention to our first figure, figure A. This is most representative of the work we do in embedded, as we want our custom application programs to interact with C and C++ libraries, a custom made device tree with our hardware description within it. And custom drivers in between. The other figures B and C are also attainable, but from different frames of reference. Potential challenges include limited thread count on FPGAs. FPGA implementation shouldn't be done on all components, which is another challenge as explained before. And how custom hardware takes time to create. The last image is simply to illustrate how our custom hardware will have custom hardware and connections to some pre-existing intellectual properties like a system communication bus or controllers. Overall, from the progress I've seen, I have high hopes and expectations for my embedded team, and I'm certain we can attain FPGA implementation on this year's ERU. Thank you. I now pass it over to Celeste.
And now we have our path to PDR. So we want to finalize our designs, begin to test, and continue our interface with MAC and MEA, complete custom software drivers and hardware images to select the FPGA-driven components, dual input control systems fully planned, and the torque and distance analysis, and our wire schematics. Thank you so much for everyone listening, and we will now open up the floor for any questions or comments you have.
I have a question. This is Marty. I was just one simple question is, did you look at how you're going to jettison the parachute, or do you have designs for that? Or is that just?
Yeah, we do have some designs in mind if Celeste want to pull up backup slide for parachute release. So for our parachute detachment methods, these are two of our potential candidates. So we have the solenoid release, also hook detachment. One of them is fully mechanical, and the other one just has to do with powering a solenoid, essentially. So I hope that.
No, this is exactly what I was looking for. Because
Okay,
depending on what you came up with, I was like, well, that might be a weight hit there. So no, that and I was just, and when you had the hiker coming up, there's going to be a little mechanism there that could get in the way. But you've thought about it, and that was my question, just right off the top. No, thank you.
Thank you so much.
And general comment, it looks like you guys have done a lot of thought behind this. Once again, great work on what you've got so far.
Thank you
So much.
Thank you. Thank you.
Thank you.
Any other questions or comments or?
I can jump in real quick. So I was curious. I know we've talked about some of this stuff offline. Obviously, I've kind of commented before that the FPGA development you guys are planning on doing is it's an aggressive design for sure. Like, I mean, I do FPGA development, at work, and it's a lot of moving parts. How much have you guys started actually like writing stuff out or testing things kind of on a board yet or anything like that?
That's an excellent question. And I'm actually happy to say this answer that we are making great progress. One issue we saw a lot with last year was that we were slow to roll on prototyping and really getting things to work and having proof that those things were working beforehand, moving on with the project. And I'd say at this very moment within my team, I have seen a lot of examples from the multitude of components. I've already seen a lot of hardware description practically done. And then those team members already moving forward with creating application programs to test that hardware layer. So I say, since it's already kind of the beginning of November, it's the end of October, I think it's great. It's great headway, and I really do think we'll get something amazing come next semester, or actually sooner than that. I hope that answered your question, Jeff.
It does. I'm glad to hear that you guys are already getting some hardware designs written out, because yeah, I mean, this is ambitious, and I like to see it. Being someone that does FPGA development myself, it gets me really excited to kind of think about how this could be integrated on the vehicle. how have you guys been working closely with the software team? Because obviously there's going to be a huge layer of interchange, right? Where, and you may have addressed this. I'm sorry, I was having some audio problems, but
Mhm.
you know, there's going to be a lot of coordination between you guys and the software team to make sure that everything exchanges back and forth between your custom hardware and your processor running your software. Or how have you guys been on the integration between the two teams?
Now, I remember this being a comment at the very beginning before the start of this year's GCP, and I know all of us leads got together and we discussed, and we really wanted to have more collaboration, to the point where we even discussed combining embedded with software altogether. But then we finalized on one concept, and one strategy was that to have joint meetings every week, every time we meet. So practically, in last year's, I'm pretty sure if you ask somebody, oh, do you know somebody from software? And they'll be like, no, I only know those from embedded. That was the situation. But now I would say just about everyone in software knows someone from embedded. They know what they're doing. They know their software solution, and they know of embedded's hardware solution to tackling these components. So if it comes to the point, especially with us in embedded, how we have hardware, a hardware layer, and we have our application layer. So what they do in software is applicable to us too, because then we can go to software and say, I know you've been working on a software solution longer than I have because I was working on the hardware, but tell me how it's been, like, how did you do it? How did you implement it? So I would say that the level of collaboration is extremely high this year.
I'm really glad to hear it, because yeah, I know, you know, one area that we could have improved on last year, and it sounds like you guys are going to this year, was there was definitely that disconnect between, you know, the embedded laying out how kind of how to interact with the hardware, but there was a breakdown between that and how the hardware was actually going to be used, right? And like how that was written. So I'm glad to see that you guys are addressing that this year. And in general, if I can make that comment for everything I've seen up to this point, I'm glad to see that the teams, it feels like you guys are definitely taking lessons from last year and learning and applying that. Like I heard a lot of talk from MAC as well, about, you know, lessons learned from last year. So I'm really, really glad to hear that you guys are making sure that you're carrying that knowledge base forward, even though, you know, obviously we want you guys to restart every year as much as possible.
Mhm.
I'm also really glad to hear that. So good work, guys.
Very much.
If there are no other questions or comments, we will move on to the next team.
I got one quick one. It's Marty again. In previous years, have you had any problems with the ERU landing upside down?
Last year we had a parachute method for the ERU, and when we've tested it, it never like flipped upside down. So we haven't had any problems. But,
okay. I was just wondering if you had a contingent. It's not in the requirements, but a contingency so your arm could flip you right side up. No, that was my final question. Thank you.
Thanks, Marty. Yeah, we haven't had an in-person demo for a couple, like 2 years now. So this year will be our first one since 2018, 2019. Anyway, so we're gonna actually take a 5-minute break just so everyone can get some water, refresh, and then we'll move on to the next team afterwards. So everyone, thank you so much for your feedback so far. It's really appreciated. And we'll be able to circle around to it at the end if there's more. But enjoy your breaks. So we'll meet back at 6 p.m.